The last time we met, we came a long way in our ability to take derivatives of functions. We were able to not only find the power rule, which allowed us to take x to any power, find the derivative of it. We then were able to find that if you have two different functions and you add them together, we can take the derivative of that addition by taking the derivative of the first function and the derivative of the second one and add them together. And that also worked for subtraction, but for multiplication and division, we had to come up with some special rules that didn't work quite like we wanted to, but at least gave us a way of doing that. We are going to have to learn a few more things that we can do to make it so that we can take derivatives of just about any function. But I thought for today we would just do something that was, again, showing you a little bit more about what derivatives can do. So if you remember the walk that I took with my wife, I think it was on video number 7 that we talked about that. We had two variables, time and the position along this path. So this was the path that we were walking on, and we decided to call position 0 is where we started on the path, and we walked along this path. And by getting a few pieces of data, we came to the conclusion that this function, s of t equals 8t cubed, described the movement along this path. Now that we've talked about derivatives, we can say, I can take the rate of change of this position with respect to time. I can take s prime of t, which we also could call in Leibniz notation ds dt, and we even have a special name for the rate of change of position with respect to time. It's called velocity. So we could also call this v of t. Now back then, we had to go through that long limit definition to find the derivative. But now that we've got the shortcut, we can say the derivative of t cubed is 3t squared, and then we have this constant out front. So we just multiply by that constant and get 24t squared. A whole lot easier than doing that long limit definition. So what do we see here? Not only was this the position, and we did this walk for 5 minutes, so our domain was 0 is less than or equal to t is less than or equal to 5. The position when t is in this domain is always positive. So we were always in a positive position along this path. We never went behind where we started. And then we can see from the velocity that this is always going to be positive too. In other words, the slopes, if we look at the slopes, they're always positive. So that means we're always gaining position as time goes on. So as time gets bigger, the position is going to get bigger because this derivative is positive, which means we never go backwards. We're always going to be going forwards. And we can even do one step further. If you realize that when you take a derivative, you're just getting another function, we should be able to take the derivative of that function. So we could call it, and this is new terminology, we could call it s double prime of t, the second derivative of position. Also called in Leibniz notation, don't worry about the notation right now, it's d squared s over dt squared. It just means it's taking the second derivative of s, and it could be called the first derivative of the velocity. And it's actually given a special name. The rate of change of velocity with respect to time is called acceleration. So I know there's a lot of different names for that. But basically what it's finding is the rate of change of velocity with respect to time. And what do we see? That from time 0 to 5, this is also positive. So that tells us something. It tells us that the velocity is always increasing with respect to time. So as time goes on, we should be going faster and faster. Our velocity is getting larger. And you can see that from the graph. Look at the slope. Not only is the slope always positive, but the slope is always increasing. So that tells us a lot about predicting what our walk would look like. We're going to be starting here. We're always moving in a positive direction, and the velocity is getting larger. We're speeding up. So this is what it should look like. Our walk should go like this and get faster and faster and faster and faster. Now, just to make it more fun, and this is a little bit of an experiment for me, but we're going to try animating this with a graphing utility called Desmos. So, if you look at this, we now can look at that little red dot on there. I hope you can see that. And when I hit the beginning, watch that red dot. It should be starting where? It should be starting here at position 0, and it should be moving to the right and getting faster and faster. So you can see at the very beginning, my wife and I are moving at a pretty slow speed, but it gets faster and faster, and we should, at 1,000, we should stop. And sure enough, it does. I'll do that one more time, just because it's kind of fun to watch. It starts out slowly, and as time gets bigger, we're going faster and faster and faster until we finally get to 1,000 meters at the end of 5 minutes. So anyway, that is an animation. So, derivatives help us predict this trip. So I'm going to talk about another trip. I don't know if you knew that, but there's a turtle that often walks along the x-axis. And there was a particular 5-hour period where I modeled the position of the turtle during those 5 hours. So, since it's moving along the x-axis, I'm going to call the position along the x-axis x of t. So t is going to be our independent variable, and x is going to be the position. And we're measuring the position in feet, and we're measuring the time in hours this time. And as it turned out, we had the turtle has a different position equation than my wife and I on our walk. It turned out to be 5 plus 3t minus t squared. And the domain was still from 0 to 5 because I watched the turtle for 5 hours. Now, this is the position. Because there's a negative sign in there, maybe for some values of time, the position is not always going to be positive. And now, the beginning where the position is 0 is not at the beginning of our path. The position is 0 is be when x equals 0, right here at the origin. So a positive position would be to the right of the origin, and a negative position would be to the left of the origin. So you can see, at the very beginning of this walk of the turtle, where was he? X of 0, the position at time 0 is just going to be 5. So it actually started right here at 5. Now, the question is, was it moving to the right or was it moving to the left? Well, one way of finding out is to take the derivative. Find x prime of t. And again, because this is position and this is time, we could call it the velocity. So what's the velocity? The derivative of 5 is 0. The derivative of 3t is 3 minus 2t. So we see at the very beginning of the trip, our position is 5 and our velocity is 3. That's a positive 3, which means the turtle is moving to the right. The x values are getting bigger. But what happens? If you set this equal to 0, you find at time 1.5 hours, the velocity is 0. The turtle has stopped moving. And then what's going to happen? Now this is going to be negative. So the turtle moves to the right, and then it starts moving to the left. And once it starts moving to the left, it's going to keep getting more and more negative. So we can kind of predict what's going to happen. The turtle is going to move to the right for the first 1.5 hours, and then it's going to move to the left. And the velocity starts out at 3 and goes down to 0, and then starts getting more and more negative. So it should be speeding up in a negative direction. In fact, if you look at the second derivative of the position, or the first derivative of the velocity, which now we know could be called the acceleration, it's just a constant. The derivative of this is negative 2. This would be in feet per hour. This is going to be in feet per hour, which says it's decreasing by 2 feet per hour every hour. And that's what it happens. It starts out at going at 3 feet per hour. After 1 hour, it's only going at 1 foot per hour. At 1.5 hours, it's going 0, and then it starts to become more and more negative until what would V of 5 be? V of 5 would be 3 minus 10, or negative 7 feet per hour. So that slow turtle is going 7 feet per hour, but in a negative direction. So with this analysis with derivatives, can we predict what this walk would look like without actually seeing the turtle? What would it do? It would move until it got to a certain place and then turn around. And we could even find out what its position was. At this time it turns around, we could put 1.5 into the position equation. I did this on the calculator, and it turns out to be 7 1/4 on the x-axis. So it would get up to right about here, and then it would turn around. And what is x of 5 at the end of the trip? That's 5 plus 15 minus 25. It ends up at negative 5. So it would end up over here. So we can predict that it's going to move this way, then move this way. And what should it be doing? It should be slowing down at the beginning, and then as the velocity gets more and more negative, it should be speeding up. So let's try this once. Let's try another animation and see if it really does that. My wife is assisting me here. But now we have to go to a different position equation. And I'm going to, if you see the little red dot, that's where the turtle is going to start, and it should start at position 5. And then it should move to the right and then move to the left. Let me see if I can make this work. Okay, so it's moving to the right and it's slowing down, and now it's turning around and moving to the left. And it should be going faster and faster and faster until it finally gets to -5, and then it stops. Since I took a little while to make that work, let me just try it one more time. So it's moving now to the right, and it's slowing down as it moves to the right. It gets to the point 7 1/4 on the x-axis, and now it'll turn around and move to the left. Okay, so anyway, I hope that takes a little bit of your time, but I hope that makes it's a little bit of fun to see that what we predicted is exactly going to be what happens. And it shows you how you have to be careful, because you started out at position 5 and ended up at -5. You might be thinking that the total distance was 10, but really it went from 5 to 7 1/4. So it went 2 1/4 miles, and then it went from 7 1/4 back down to -5. So all total, it went 14.5 miles. So you have to be careful that you find out when the turtle or whatever it is that's moving, where it stops and maybe turns around. You can't just take the beginning position and the end position to get the distance. Well, now let's move and talk about another type of movement. In physics, they would call this free fall. So if you take any object and drop it, or throw it up in the air or throw it down, it's going to move according to some position and time equation. So in this case, let's call that S of t. And this time, let's call S equals 0, because we need a reference point, just like we did for the path that my wife and I walked on, and the reference point was the origin on the x-axis for the turtle. In this one, S equals 0 is going to be the ground, and t equals 0 is going to be the time that we start the object moving up or down. So, what is going to affect the position of anything that's moving in an up and down manner in free fall? Well, first of all, the initial position. So I can call that the position at time 0. Since that is a constant, it's sometimes called S0 in physics. Now, what else is going to affect the position? Well, if it's not just dropped, if you're throwing it, it's whatever velocity your arm has, if you're throwing it with your arm, at the time you let it go. So that's called the initial velocity. So that's called v sub 0 times t. So if you take so many feet per second and multiply it by seconds, that's going to give you the change in position during that time. And that's all that would affect the movement, except for this invisible force that we have called gravity, which tends to change the velocity at a certain rate. So I'll be able to explain this better, where this equation comes from, but this affects the upwards movement in a negative way. It's always bringing things back down to wherever the surface is you're on, and it turns out to be, again, I'll explain this in more detail later on in the year, but the position at time t has to do in a positive way with the beginning of position, in a positive way with the velocity at which you're throwing it, but in a negative way because of gravity. Gravity is going to pull it back down to the surface. Okay, so I'm going to tell you something about me that maybe you didn't know, that I don't have too many talents, but one of them happens to be I have really good leg speed. I can really move that leg when I kick it. So if I take a ball and kick it, it goes up pretty high in the air. My leg speed happens to be 320 feet per second. So let's see if we can model what a ball would look like at the time I kick it. By the way, most people, when they punt it like a football, they punt it from about their waistline, whereas I do it right from the ground. So I can say that my initial position is 0, because I start kicking it right from the ground, right here, in an upward manner, and my initial velocity is that leg speed of 320 feet per second, and on Earth, this gravitational constant is 32 feet per second. Gravity slows down your velocity by 32 feet per second every second. So this would become 1/2 of 32, or 16t squared, and we have a position equation for the ball once I kick it, where t is time and s is the position above the ground. So let's see how high the ball gets. Well, to see how high the ball gets, what I want to do is find its highest spot. Well, I don't know if you can see this, but if I throw something up in the air, the highest spot is going to be when the velocity equals 0. Well, if I take the derivative of the position and get the velocity, I now have a velocity equation. And when is that going to be 0? If I set that equal to 0, I see it's at t equals 10 seconds. Because s is in feet and t is in seconds in this equation. So, how high does it get? Well, if I take that 10 seconds and put it back into the position equation, I get 3,200 minus 1,600, or 1,600 feet. So it gets about 1/5 of a mile up in the air when I kick that ball. So if I can ever figure out how to kick it at an angle, because when I kick it, it always goes straight up in the air, maybe I'll get a new career as a punter in the National Football League. But right now, I'm just happy teaching calculus. So anyway, that's how high it gets. And if you took the second derivative and got the acceleration, what do you get? The derivative of this is just negative 32 feet per second. And what does that do? This is due to gravity. Gravity is slowing down that ball at 32 feet per second every second. So it starts out at 320. In 10 seconds, it's going down 32 feet per second every second. That's why it stops after 10 seconds. And now we should be able to model that one more time on this graphing utility. I don't know if I told you it's called Desmos that I'm using. We should be able to go to one more of these. And now the ball is starting right at the origin. And I'm going to try for 20 seconds, because 10 seconds to go up and 10 seconds to go down. Now look at the ball. As it's going up in the air, it's slowing down, and it should get to 1,600 feet. And when it gets to 1,600 feet, now it starts falling down again. And as it's going down, it's going more and more negative, so it's actually speeding up. I'll do that one more time and then we'll be done with these animations. So as it's going up, the ball is slowing down. It gets up to 1,600 feet, and now it's going from a 0 velocity to a -32 to a -64. By the time it hits the ground, it'll be going at a -320 feet per second. And I wouldn't want to be the person under there trying to catch it. Okay, so I think we've talked a lot about applications of derivatives when one variable is position and the other one time. And this is a really important application. But really quickly, before we end today, I wanted to do one example where the variables weren't position and time. So this time, I'm going to talk about a new product, a new high-tech product that I would like to make in a factory. And I would like to sell it. So this time, I'm going to let X represent the number of items that I'm making. And up here, my other variable is going to be in dollars. So I want to know, first of all, the cost to produce X items. So I'm going to give you a little bit of an economics course. If you produce no items, it's still usually going to cost you a little bit because you're already starting by renting some type of facility to make these in. So you're going to have some fixed cost. Now, at the very beginning, so we're going to have some kind of function called the cost is a function of how many items you make. So we could call this variable C. Now, what happens if this is in dollars and this is in items? What happens when you take the derivative? What are the units going to be in? The units are going to be in dollars per item. Not feet per second, they're going to be in dollars per item. That actually has a special name. It's called the marginal cost in economics. And that's basically the cost per item. Now, that first item you produce is going to cost quite a bit because you've already had to hire somebody to make that item and you've turned on the lights in the factory. So that first item is going to have a really steep cost per item. It's going to have a high slope. But then, as you keep producing items, the more you produce, obviously it's going to cost more money, but the slope, the marginal cost, is going to get less until you get to a much more efficient rate of production where the slope is pretty small. Now, once you hit that spot, the maximum efficiency, then all of a sudden, if you try to make more, your assembly lines start to break down. You have to pay your workers overtime. So now the cost per item starts to go up again. So I'm not saying every cost function will look like that, but that's a pretty typical one. But we're also interested in the revenue. So I'm going to model both of these on the same graph, because the revenue is also going to be measured in dollars and items. So if you don't sell any items at all, you have a zero cost. But especially if you come up with something that people really want, at the very beginning, if you take the derivative here, you're going to get dollars per item. You're going to be able to sell that first item for quite a bit because everybody wants to buy it. So you're going to have a steep marginal revenue. So at the very beginning, it's going to be steep, But the more you make, the less you can make per item. So a typical revenue curve might look something like this. Now, your question would be, where would you like to, how many items would you like to make? You wouldn't like to make this many items right here because your cost is higher than your revenue. Right here, the cost and revenue are the same, so that would be a break even. So isn't this the spot right here? This is the number of items you'd like to make right here. Now, I don't know if you're seeing anything, and I'm not proving this right now, but look at it. What do we see at this point? The marginal revenue and the marginal cost turn out to be the same thing. So maybe it's going to turn out that the maximum profit happens when the marginal revenue equals the marginal cost. So anyway, we'll explore this more in the future, but the purpose of today was to try to get you excited about all the things derivatives can do, and in the next couple of talks that we have, we'll go back to learning a little bit about how to find derivatives even more efficiently. So, thank you. Hope you enjoyed it.